Hello and welcome to Internet Day San Francisco 2026. I'm your host, Ron Petty. Internet Day is brought through a partnership by the Internet Society San Francisco and SF Bay ACM. We would also like to thank the continued financial support from RXM and Minimum Distance. The agenda for Internet Day San Francisco goes as follows. We'll open with a discussion about what Internet Day is. Then we will talk about Project Nanda and how it is paving the way for agents on the internet. Next, we will talk about routing machine learning inference traffic at internet scale. Then we will pivot to the hardware networking layers through IPv6 virtual networks as the universal hardware abstraction. And then finally, we'll talk about Q-Day, which is an event many are predicting when encryption will be in trouble. We'd like to thank our speakers for this event. We appreciate their time and their effort. If you would like to participate in Internet Day in the future or any of the events related to the ACM or the Internet Society, please email us at support@sfbayisoc.org. So, in support of the internet, what exactly is Internet Day about? So again, my name is Ronald Petty. I am the current chair of the Internet Society and ACM chapters here in Silicon Valley. My day job, I am a consultant at RXM. So what is Internet Day? So Internet Day is a global celebration of the internet. Celebration is only part of it though. We also need to collaborate, to communicate, to share, and support the internet. And so this is our attempt here in San Francisco to do just that. By highlighting some of the local talent we have here in the Bay Area, talk about the deep technical expertise they have and are willing to share, and that is really the goal of Internet Day San Francisco. We hope that these talks will inspire you to participate in the future, or at the very least, learn something new and help others. Let's go ahead and get started, and thank you for coming. Welcome back. Next, I'd like to introduce Mahesh Lambi. The internet was built for hosts. Nanda is built for agents. The internet was designed around hosts, domains, addresses, APIs, and human-driven interaction. That architecture still matters, but autonomous AI agents introduce a new kind of network participant, dynamic, task-driven, capability.
Hi, this is Mahesh Lambe from projectnanda.org. Nanda stands for Network of AI Agents in a Decentralized Architecture. And we are architecting the new kind of an internet called Internet of AI Agents. So take a pause for a moment. So most revolutions do not arrive wearing the clothes of a revolution. They arrive as a technical inconvenience. The early internet did not look like a civilization infrastructure. It looked like machines learning to talk to other machines. And the web did not look like a media empire. It looked like a documents with links. And now we are at the kind of a moment again, like where autonomous agents are coming onto the internet. They're not coming as a pages or not as apps, not as a passive endpoints. They will discover, negotiate, delegate, verify, and act. So this talk is not about replacing the current form of the internet. It is about asking a much bigger question. What does the internet need to become when its next major user is not always human? That is the question Nanda is built to explore. So I want to begin with a simple shift in perspective. For most of our lives, we imagine the internet as something humans use. As human, we open a browser, we type, we search, we click, we compare, and we decide. But agents change the shape of that story. An agent does not have to browse like a human. It can search across services, call tools, and ask other agents for help, compare outcomes, check policies, and return with evidence. That sounds like a product feature when there are around 10 agents, but it becomes a network problem when there are tens of billions of AI agents. So the real question is not, can agents use the internet? Of course, the agents can use internet. The deeper question is, will the internet know how to recognize these agents or trust them or route them and coordinate them without trapping them inside a closed platforms? So here is the line I keep coming back to. If you follow the protocol, you can participate. That was the rule for the current form of the internet. That is almost a moral sentence disguised as engineering. It meant you did not need to own the network. You did not need to be born powerful. You did not need permission from one empire. You could just connect to the internet. You could publish the content on the internet. You could build, you could trade, you could be discovered. This is why the internet mattered, not because it was fast, not because it was cheap. Those things helped, of course, but the real magic was that it gave the world a common foundation without a single landlord. So now agents are arriving. These are autonomous AI agents with its own reasoning capabilities, and we have to ask whether they inherit the same open foundation or whether they are born into a world of private kingdoms. So think of it like the internet keeps changing its main character now. Agents are the main character. It's going to be an agent centric internet. So first machines had to talk, then documents had to link, then people needed identity, then services needed APIs and cloud infrastructure. So each transition looked obvious only after it had happened. So before the web, connecting documents globally felt strange. Before social networks, putting human identity at the center of the internet felt totally strange. Before APIs, letting software talk to another software at scale felt totally strange. Now, autonomous agents create the next turn. So they are not merely another application category, they are a new kind of a participant. And every time the internet gets a new participant, the infrastructure underneath has to evolve. So, so, so just remember, agents do not just browse, they act. So this is the behavioral break. A human searches, an app calls, an API responds. An agent may do all of that and more. It may discover who can perform a task, decide which tool is appropriate, negotiate cost or latency, check its policies, call another agent, verify the result, and explain why it chose that path. That means agents will create far more small and distributed interactions than humans could do. And because they act on behalf of people and organizations, the stakes are much, much higher. Discovery is not just a convenience, or trust is not just a badge, or routing is not just a performance issue. But for agents or AI agents, these become safety, governance, and market structure problem. So, so the old model was request and response model. Like the classic internet interaction was beautifully simple. A client asks, a server responds, a browser asks for a page, an app calls an API, a service returns a data. But agentic interaction is a richer question. An agent is not only asking, where is the endpoint, but rather it may be asking, oh, who can complete this task under my constraints? Which capability is verified, which agent is authorized, which route is compliant, which interaction is safe right now. So that is a very different architecture. So we are moving from request and response to a delegation and coordination. So that's very important line. Like we are moving from a request response model to a delegation and a coordination model in an internet of agents. And once you see that, you realize why a simple directory or a static URL is not enough for the agentic web. So DNS was a miracle because it answered one hard question, you know. So where is this name? So I want to be careful here. DNS is not the villain in this story. DNS is one of the most elegant pieces of infrastructure that was ever built. It gave the internet a naming system that humans could use and machines could resolve. It answered a hard and necessary question: what is this name, or where is this name? That abstraction helped the internet become usable at a global scale. So without it, the web as we know it does not exist. But every infrastructure layer is born to answer the question of its own time. So DNS was designed for names, hosts, and locations, but the AI agents bring new kind of a questions like agent identity, capability, agent trust, policies, revocation, context, and dynamic routing. So the point is not that DNS is insufficient. The point is that the internet has a new problem or a new set of problems to solve for the agents. So agents need more than where question that DNS had already solved for the internet or the current form of the internet. So agents need a richer question than where. So if I am an agent acting on behalf of a hospital, a bank, a government department, or even a person, I need to know much more than the address of the service. So I need to know who is this actor who controls it, what is it allowed to do, are its claims verified, which endpoint is safe right now, what policy applies, can this access be revoked? So there are, and these are not academic questions. They are the difference between a useful agent ecosystem and a dangerous one. It's because once agents act across boundaries, location is only the beginning. So the agent is not just an endpoint; it is an actor. Um, so think of like the current URL is not a passport; it's just an address. So one simple metaphor helps here. Like URL is not a passport. So if you know my street address, you do not know who I am, you do not know what I am authorized to do, you do not know whether my license is valid, you do not know whether my credentials have expired. So for AI agents, which is having a reasoning capability, we need something closer to a passport. So not a marketing profile, not a static API page, or something else, but verifiable facts that travel with the agent, like its agent identity, agent ownership, its capabilities, credentials, its endpoints, its policies, and revocation state as well. So that is why the agent facts idea matters. Before one agent trusts another, it needs facts it can verify, not promise it has to believe. So few agents are a product feature. A billion agents are an internet problem. So scale changes the category of the problem completely. A single chatbot is a user experience problem. A handful of enterprise agents are integration problems, but billions of agents create an internet scale problem. At that scale, we need shared answers for naming, discovery, authentication, capability verification, routing, revocation, auditability, and governance. If every company solves this alone in silos, what we get is a duplication, fragmentation, or vendor lock in. So we get fragile systems that cannot safely discover or trust each other. So this is the moment where product design becomes infrastructure design at an internet scale. And that is the moment Nanda is trying to meet. Um, Also, without an open coordination, we do not get an agentic web. What we get is a private kingdoms. So this is a strategic risk. If every major platform creates its own agent identity, its own registry, its own trust model, its own routing layer, and its own rules, we do not get the agentic web. What we get is all private kingdoms or walled gardens. So each kingdom may be powerful, each may be polished, it may be useful, but the deeper promise of the internet is lost. Yeah, definitely the deeper promise of the internet will be lost if we don't make it right. The web became extraordinary because links crossed boundaries. Email became extraordinary because it could move across domains. APIs become extraordinary because they could compose across services. So if AI agents cannot cross boundaries with identity, trust, and policy, then we have not built an internet of agents. Rather, what we have built is a feudalism with APIs. So Nanda is an open coordination layer for autonomous agents. So this is where Nanda enters the story. So Nanda is not simply a registry. A registry sounds like a list or a database, but the ambition is much, much larger. Nanda is exploring an open coordination layer for autonomous agents at an internet scale. How they become discoverable, how their facts become verifiable, how endpoints are resolved dynamically, and how different ecosystems can interoperate without one platform owning the entire map. So the important phrase is open coordination. Agents need shared ways to find each other, trust each other, and route to each other. But if that layer is owned by one vendor, the agentic web is compromised before even it begins. So Nanda's role is to push forward an open, or rather push towards open infrastructure for this new actor on the internet. So, so the first primitive that we are trying to solve is the discovery. Uh, that's called Nanda index. So if agents cannot discover across boundaries, the ecosystem collapses into silos. But discovery cannot simply mean one company owns the list. The Nanda index points towards a different idea, more or like a federated discovery, a way to locate agents and their associated facts across ecosystems without requiring one platform to become the landlord of the agentic web. That matters. That definitely matters because agents will not all live in one place. Some will live inside enterprises, some with cloud providers, some might be at the edge or the physical AI devices, some with individuals or very much personalized ones, and some inside a public interest networks. So the discovery layer has to respect that reality. So the goal is not one giant database, the goal is a network of discoverability. So remember, the goal for Nanda Index is a network of discoverability. The second primitive is that verifiable facts. This is where agent facts become more powerful. The agent should not only say, trust me, it should carry facts that can be checked: identity, ownership, capabilities, credentials, endpoints, policies, expiration, and revocation. For humans, we have institutions around identity. So for companies, we have registrations, contracts, certificates, and compliance processes. Agents need an equivalence of trait that works at a machine speed. The phrase I like is this: the agent carries facts, not just vibes. If one agent is going to delegate to another or allow access to a tool or exchange sensitive data, trust cannot be a slogan. It has to be a portable, checkable, and revocable. I'll repeat. So the trust cannot be a slogan. It has to be a portable, checkable, mean verifiable, and revocable. The third primitive is adaptive resolution. In the old model, resolution often feels like lookup. You have a name and you resolve it to a location. But agent interaction happens in a living world. The right endpoint may depend on geography, latency, cost, load, capability, security posture, data boundary, or policy. The best route now may not be the best route 5 minutes from now. So I repeat, so that's why the dynamic resolution becomes one of the very much important factors. And that is why the adaptive resolution matters. For agents, resolution becomes a decision, not just a lookup. So this is a subtle but important shift. It means the network is no longer only answering, where is it? But rather it is helping answer, what is the appropriate path for this interaction now? And this is important. Nanda should work with the internet, not against it. So the existing internet is the ground. DNS remains essential. TLS remains essential. HTTP APIs, certificates, and cloud infrastructure remains all of it essential. So Nanda is not trying to reinvent. It is asking what has to sit above it when the thing being discovered is not merely a host, or a page, but an autonomous actor. So the most accurate frame is extension, not replacement. The internet gave us reach. Nanda explores how agents can add identity, discovery, verifiable facts, and trust-aware coordination on top of that reach. Enterprise will not ask for magic, they will ask for a control. So the enterprise adoption will force the discipline. Enterprises will not allow random agents to roam freely because the demo looked impressive. They will ask basic and hard questions. Who is this agent? Is it approved? What data can it touch? Which tools can it call? Who is liable if it acts? Can we audit what happened? Can we revoke access immediately? Can this work across vendors? These are not obstacles to innovation, they are the conditions for production. So, if we want agents to move beyond demos and into serious environments, we need an infrastructure that makes them visible, verifiable, controllable, and interoperable. This is important. So, we need a new kind of an infrastructure that makes agents visible, verifiable, controllable, and interoperable. No visibility, no trust, no production. Just remember this. There is a governance question hiding inside this technology. Whoever controls discovery controls visibility. Whoever controls trust controls participation. Whoever controls routing controls the market. So remember this. That is why this cannot be treated as a narrow engineering concern. If agent discovery, identity, and trust become private toll roads, the agentic web becomes a captured before most people even understand what happened. So the open coordination does not mean no rules. It means shared rules, interoperable rules, rules that let many parties participate without surrendering the future of one platform. The early internet understood this. The agentic web has to remember it. So the future of agents will not be decided only by model intelligence. If there is one idea I want the viewers to take away, it is this. The future of agents will not be decided only by model intelligence. Of course, intelligence matters, better reasoning matters, better tools matter, better user interfaces matter. But the larger question is participation. Can this agent be discovered? Can it prove what it is? Can it show what it is allowed to do? Can another agent trust it? Can an enterprise govern it? Can it operate across boundaries without being trapped in one platform? So, a brilliant agent inside a closed silo is still limited. The real breakthrough comes when agents can safely participate in a larger world. The internet gave humans a shared world. It allowed us to publish, search, connect, build, trade, organize, and discover each other without one central owner controlling every doorway. Now, agents are becoming actors in this world, and we have to decide what kind of a world they will inherit. Will it be open or closed, interoperable or fragmented? Is it trustworthy or chaotic? Is it public infrastructure or private capture? So, this is why Nanda matters. Nanda is not trying to replace the internet or the current form of the internet. It is trying to help the internet absorb the next major participant. The first internet connected machines, the web connected people and information. So the Nanda is helping the next internet connect agents without losing the openness that made internet matter in its first place. That is the work, that is the invitation, and that.
Welcome back. I would like to now introduce our next speaker, Rajat Shah. Machine learning model traffic routing at internet scale. Learn how traffic routing for ML models poses unique challenges at internet scale and how Netflix solves them through specialized software design patterns. Learn how various API gateway solutions over REST, service mesh, and custom design can help you scale traffic routing for efficient ML model serving. We will also go into how various experiences on Netflix.com are powered by unique ML models.
Hello, everyone. Welcome to Internet SF Day 2026 event. I'm Rajat Shah. I'm a staff software engineer at Netflix, working in the AI platform organization, building large-scale distributed systems. Today, in this presentation, we are here to talk about routing requests in a machine learning model platform at internet scale. This presentation is based upon a blog post that we recently co-authored on the Netflix official technical blog, which I would encourage you to read in order to get more insights. Every time you open Netflix, a set of machine learning models decide what you see. This infrastructure is very complex and typically works in a very harmonious way in order to provide you a seamless experience that you get. This presentation is mainly to talk about a key component of that infrastructure, which is tailored around how a request routing takes place at this large scale. Netflix has millions of members. Many of them visit Netflix at the same time. And as a result, when there are hundreds of machine learning models powering the various aspects of your experience on the Netflix application, the overall number of requests that a machine learning inference platform ends up receiving tends to be close to 1 million requests per second, which is very large. And that's why the scale of the problem that we are going to go into tends to be very sophisticated. We have three primary agenda topics. One, why does ML routing, traffic routing is harder than it looks? Second, we'll talk about few protocol choices that shape the overall architecture. And third, we'll talk about two patterns of routing at scale and the trade-offs between them. So let's first talk about the routing problem and how it specifically applies to machine learning model traffic. As I was mentioning, whenever you open Netflix, there are several dedicated machine learning models powering your specific personalized use case. For example, a use case can be to display the right ordering of continue watching row on your homepage. It can make use of lots of your previous viewing history information, also what are you most likely to watch in a given moment. All of that feeds into a dedicated machine learning model that decides what should be the ordering of TV shows or movies on the continue watching row. Likewise, when you start typing a search query, a set of personalized models decide what search results to show as you start typing each letter of your query. The homepage rows themselves are also very personalized. So the ordering of the rows, the kind of rows that you end up seeing, such as in this example, romantic comedy movies, is an indication that you like and have preference for such movies. And that's why Netflix will choose to display that dedicated row for you. And it's not just movie and show personalization. Behind the scenes, lots of services make use of machine learning to make the right decisions. For example, at the time of charging you for payments, it can make it can verify that the payment transaction that's happening is actually legitimate and not a fraudulent transaction. In short, lots of machine learning models work in harmony in order to power the end-to-end seamless experience that you got on Netflix. To give you a little bit idea and a very high level view of what this typically looks like, it's very illustrative in nature and far more simplified than what in reality happens. But you can imagine as you open Netflix or you start interacting with any aspect of Netflix application, be it your web browser, TV, or mobile, the first thing that happens is that client makes a request to an API gateway. Which will do some basic things like authentication, making sure you have the right membership tier in order to show you the right experience. That request can then flow into a set profile service that can retrieve your profile information, maybe your historical viewing information. And if you're, let's say, typing search, that request can route to the search system, which is going to retrieve the right title based on your search query. And then all of that can be fed into a recommendation system that is going to rank the titles in the right order so that you are most likely to click on the first title based on your all the information that the platform has about your taste and your likelihood of playing a title at that given moment. Like I said, this is far more simplified. In reality, there could be thousands of services, microservices, as we call it, interacting together, making requests to each other in order to perform some specific part of your overall request and to serve you the end experience that you get. So this is an example of how requests typically travel from clients to API gateway to several backend services. Now, typically, there are two ways to solve it. One is a monolithic architecture, which is you build one single monolithic application that is able to do, let's say, authentication, search, recommendation. But it's very hard to scale them, as you can imagine. If the single application is responsible for so many different tasks for a user, it's hard to maintain and evolve it and scale it as the complexity of the system evolves and as your number of users increase. That's why we highly leverage an architecture pattern called microservices, where each service is very much dedicated to solving one problem and solving that problem very well. So that means there could be a dedicated service that is just for reliably and safely with proper authentication and authorization, retrieving the profile information. There could be another service that is purely responsible for retrieving the search information. It ends up being thousands of independent services, each doing its own job. These services talk to each other over the network dozens of times as your request flows. So for a single user, for a single request, there could be hundreds of services that are in that request path in order to serve you the experience. It's important that that many of these experiences these days require ML model, because the kind of problems many systems are dealing with end up very well suited for machine learning models to be able to learn, train, and eventually help optimize the experience and make very personalized and very good data-driven decisions, and not some business logic or heuristics that can solve these problems. And as the request flows, each ML model call needs to reach the right machine learning model as well. These can be hosted on various different compute clusters. It's important that it lands on the right cluster, not just for the right title recommendation, but these models could have very different purposes, very different objectives that it might be optimizing for. So they need to reliably be, these requests need to reliably be reaching the right place in a very low latency sensitive manner. I think this is a key thing to note throughout this presentation is lots of optimizations and architecture patterns that we will be describing will very much be centered around how do we keep the overall latency, which is described as the amount of time it takes for an action to perform, to be as low as possible. Your likelihood of enjoying the end experience that Netflix provides you over these various different client applications is very much dependent on how responsive and how fast is that application. And that's what we call as latency. Now, how is this problem related to machine learning, traffic routing, and why is it hard? Machine learning models tend to be massive. They have very high memory consumption because they are trained on real data, and it builds in memory neural networks or weights that it uses in order to make decisions for a newer data point that it might have seen. So as you train your models, as the model complexities grow, the neural network models, for example, can have like several gigabytes of memory consumption when they load in a given service. As the number of use cases for machine learning grows, there could be many different machine learning models that are powering even a single experience, because as the researchers iterate and optimize their machine learning models, they typically tend to do A/B experiments and validate the hypothesis with different data points and with real user collected data. So it's not just like handful of 10 to 15 models, but in reality, hundreds of models that are distributed over thousands of compute clusters in order to power this entire machine learning based experiences on Netflix and other platforms. In addition, the topology of these services also tends to keep changing. The way in which these clusters are placed together right now, it could be evolving over time, and it keeps evolving over time because the model is innovated upon, and the memory and resource like compute needs for these models keep growing over time as well. So one way to solve this problem could be a very simple approach, right? You could just hard code the end VIP address of a user, as we show in the left-hand side of this slide, and simply put it in the code base for all the client. In this case, now we are starting to use client as a user of the machine learning model service. So client could be actually just an internal microservice that we showed in that initial graph, not the end user application. This is more of an internal microservice that needs to interact with the machine learning model microservice. But the problems with hard coding are very straightforward, right? As I mentioned, the topology keeps changing, the IP addresses or the domain names will keep changing, and you want these client applications to not have to change their code base every time this changes. Imagine at the scale of Netflix, with the number of microservices that we have, it could be very much a bigger overhead if and every time the topology changes, you have to coordinate with so many services to get the changes propagated. Instead of doing this, wouldn't it be nice if the clients could simply say that, I don't know where to go for getting the rankings for continue watching row, but I'm just going to say that I want this specific use case fulfilled, and some central configuration which maps the use case to the virtual IP addresses could take care of actually resolving the correct IP address and sending the request to the correct machine learning model. So that's typically how we end up providing an excellent abstraction for all the different clients that need machine learning based experiences to be powered. So we described the problem. Now let's talk about the key aspects of what shapes the solution that we'll be going into. One is the protocol choice. What kind of protocol are we going to use in order for these microservices to interact? And there are two very popular ones. One is called REST, which stands for Representational State Transfer, and another is called gRPC, which stands for Google Remote Procedure Call. And to quickly show what these two options look like, on the left-hand side, we'll quickly describe what REST looks like. It's a very popular protocol for interaction between a client. To go back, client is, in this case, it could be a mobile TV browser, but a client now can be a different microservice as well. So not something that the end Netflix user sees, but an internal backend service that the Netflix platform might be using in order to interact with another service. So REST, which is backed on HTTP, works for pretty much all kind of system-to-system communication needs. A web browser can interact with a backend API gateway or a service through REST, as well as internal services, microservices can interact with each other through REST. It's a very simple JSON human readable. XML is also supported, but JSON is the most popular way of communicating between different services when you use REST. It works everywhere, like I just mentioned. It has some nuances though. It's a little bit verbose. It is human readable. It typically doesn't get encoded and compressed in order to send it over the network. And JSON overall is a little verbose as well. If there are multiple repeated keys, the overall JSON request payload body could be pretty huge, which is not very ideal when it comes to building such large distributed systems. So because our problem is primarily around service-to-service communication and optimizing all the internal microservices to interact with the machine learning model services efficiently, gRPC or HTTP2 is actually far more suitable. Like I was mentioning, it's a remote procedure call based framework, which basically looks like in a typical client service. It looks like a local function call, but it's actually a remote function call to a different service over the network. It has very good ways of optimizing the request payload size so that the end data that gets transferred over the network when the communication initiates between two services is actually far more smaller. It has great streaming protocol support as well, which allows a client service to easily get the response as the response is being produced without waiting for the entire response to be ready. HTTP2 has its own benefits. It's the successor of HTTP1, and it allows for multiplexing. So overall utilization of the network bandwidth is far more optimal with gRPC. So why does machine learning model actually end up using gRPC and liking gRPC a lot? Like we said, the problem we are dealing with is actually service-to-service communication, which needs to be optimized. And machine learning is a very typical case where the payload size is actually huge. In this example, though it's a far more simpler representation, the request payload can actually contain a lot more details about the user's viewing history, the videos that you like, the videos that you dislike, what you have seen, videos that you that were shown to you but you did not end up playing. All of that information needs to be transferred over the payload in order to make the machine learning model inference make the right decision. So the overall structure is huge. And if you see in this example, if we chose a REST or JSON approach, it ends up, this request payload ends up taking 68 bytes. But if you were to transfer the same information over the wire in a different format, which is called protobuf, where it translates into a binary format, so not very human readable when it actually transfers over the network. In this case, it ends up being just 18 bytes instead of 68 bytes, which is a huge cost saving. And like we were mentioning earlier, latency is very important in these interactions between services. So the amount of network bandwidth that you can save through this is quite significant. The other benefits like streaming, HTTP2, we already mentioned. Schema is also pretty important. You want very good handshake between the client service and backend service for what should be the type of user ID, what should be the type of title IDs. All of that is important. And JSON is very loosely coupled. You don't mention what is the type of a string explicitly. And sometimes the number of types that are available are also very limited. With protobuf, you can say integer, double, long, and all of those types are explicitly defined, as opposed to in JSON, where you just have a general integer type and you don't explicitly say the type. And you can have very loosely coupled types as well, where certain keys are integer, certain keys are string. So all of that ends up being a little bit problematic for these large-scale microservices, and gRPC type schema checking is actually far more better and safer as well, and more reliable. So because it applies very well to machine learning, we realize that the most popular API gateway solutions out there, which we'll just start talking about, are actually built for REST. And we wanted something that works very well with gRPC. And that's this choice of protocol, that we want to go with gRPC protocol because of all the benefits that I just mentioned, forces us to commit to certain architecture patterns. So let's talk about these patterns. There are two primary patterns for routing requests at scale, and we'll talk about them, talk about the trade-offs between them. One is called API gateway and another is called service mesh. Let's see what is API gateway. So API gateway pattern looks like this in practice, which is you have a central single entry point into your system, and all the clients that need to interact with your compute clusters need to go through this central service. There are popular API gateway solutions. AWS has an offering as well, which allows you to do this thing at scale. And we did start with that as well. So machine learning traffic, we considered, because we needed gRPC, however, we built our own service. In this diagram, it is displayed as switchboard, which is this orange block. It is the API gateway pattern, where clients now only have to interact with one API gateway or like a service analogous to API gateway, and client can just specify the use case name, for example, continue watching row, and this central service is responsible for resolving the right IP address or the virtual IP address for the correct compute cluster to go to. And it pretty much actually functionally solves several of the initial requirements around context-based routing, clients not having to know the changing topology of all of these clusters when things evolve, because all clients have to do is keep interacting with this middle layer, and things should ideally work. Well, it did unlock, like I was mentioning, several of our initial problems. Context-based aware routing, it provides you a very good centralized way to also manage your traffic. If you were to gradually shift traffic between clusters, you can do it through this central compute cluster or an API gateway. Lots of observability is also baked in because your entire machine learning traffic is flowing through this one central service. You could benefit from building and maturing this central service and getting all the benefits applied immediately. The clients also don't have to do much routing information storage, because all they have to do is know how to interact with this API gateway and they're good to go. So, like I was mentioning, it functionally solves most of the problems until when your traffic scales really large and your traffic is huge. That's where the problems start showing. And it started showing once we started hitting almost 1 million requests per second. And I think some things might be obvious here, but it started showing two very critical problems to us. The diagram here, I think, is displaying the exact problem that I'm going to convey now. The gateway now is becoming a single point of failure to our system. If that gateway goes down, all the clients that relied on machine learning experiences have to now do something smartly and differently. They have to have some fallbacks or degraded performance, or they might stop performing altogether if machine learning was very critical to their experience, which is not ideal at this scale. If all the requests are actually going through this shared gateway, and if you can imagine, a gateway might look like, to draw an analogy, it might be a pipe through which all the requests are flowing, but that pipe has some limited constraints, limited CPU, limited memory. And if a single client, let's say a client A in this case, starts sending very large bursty traffic, it might occupy most of the network bandwidth that was available in API gateway. And as a result, the client B and client C end up seeing some degraded performance, even though they didn't do anything wrong. So this shared aspect of API gateway makes it very hard to scale it properly and provide very good isolation between the different callers. The other problem that it showcased is around latency. And like I mentioned, latency is super critical in these use cases. And because gateway exists as a middle layer between the client and the model service, it essentially entails an additional network hop, which could take up to 10 to 20 milliseconds. It is not acceptable for systems that powers hundreds of machine learning models, because this latency multiplies and it could have an overall degraded impact on the user experience that you are providing. So that forces us to think of different options. We already established that gRPC is the way to go for optimal communication between two services. And we have established now that API gateway solution, even though it functionally works, it has problems at scale that are very hard to solve with that architecture pattern. So if you look harder at this problem, you realize there are actually two sets of problems that are mixed up together through that API gateway solution. One is where to go. That's a simple problem of routing. And the second problem is what to send. That's the actual request payload size, which is the amount of information that you're going to send to the machine learning model service in order to make a decision. And we need to decouple these and solve these separately. And that's where this next design pattern comes into picture. Think of it as a directory assistance pattern, where if you need to reach out to your friend, you can look up a number in a directory service. And once you get the number, you can close the directory service and directly make the call to the to your friend. Slightly different from the API gateway pattern, where there is an operator pretty much sitting between you and the friend, and the operator is responsible for being present at all times so that the communication can happen seamlessly between the two communicating parties. Uh, Service mesh is a pattern where essentially you have, like I was mentioning, it acts as a directory assistance pattern, but to put it in more technical terms, it lives as a site local proxy coupled with a sidecar. It can basically directly have the client get the information in order to make a direct communication to the backend service without a middle layer in between the between the client and the service. Sidecar handles routing, retries, observability, so all the benefits that API gateway provided could actually be done here as well. Plus, it is decentralized in nature. Envoy is a popular open source implementation of service mesh. It relies primarily on request headers in order to make the requests go to the right destination. Plus, you can configure it actually in very dynamically without having to have applications or client services restart for any routing rule changes. Plus, it handles all service-to-service traffic at Netflix already. All the microservices that we have internally already have these local proxies running in order to make the communication happen. It has built-in tracing, observability, and all the benefits of API Gateway. So why does it matter for machine learning? Like I was mentioning, if you split the problem into two, one is the client asks the sidecar, where should I send this request? And a sidecar answers, okay, based on the information that you provided, which is this user ID, this country, and n number of attributes of the user or the device, this is the machine learning model cluster that you need to interact with. That information is all that it needs in order to get to the right machine learning cluster. Then the local proxy, the Envoy service mesh proxy, which is running in the client or the host application itself, can read this information and which is available in the header in order to send the request to the right cluster. So in this case, there is no middle layer at all. And I'll show you through a diagram what this essentially ends up comparing against with the API gateway. So like I was mentioning, think of a mental model or an analogy of an operator versus directory assistant. API gateway as an operator, it sits in between the two communicating parties, and it needs to be there at all time and be present at all time. Whereas the service mesh pattern that we just described is actually a sidecar-based pattern where you just ask the information once, and then you use that reliable information, cache it locally, and use that cached information locally in order to directly communicate with the model cluster that you are interacting with. What this essentially means is that now there is no system sitting between the client and the model that is in the request path or in the critical path, as we call it. And these systems can continue communicating with each other without the need for a third system to be present and available and be reliably available at all times. It saves a lot in latency as well, because you don't have to go through that additional network hop as well in order to get the model inference done. So key takeaways, these problems are actually beyond just Netflix and machine learning. You have essentially these patterns visible in internet terms as well. And I'll just quickly map these very common internet patterns to our problems described so far and the solution that we came up with. So if you look closely, the use case pattern which I mentioned, which is the calling infrastructure should only need the minimal information, which is continue watching row, and the actual IP address resolution can live somewhere else. That's exactly what the domain name service or DNS does. When you type google.com in your web browser, you could just type google.com and it and internally DNS can resolve to the right IP address, which will serve your request. Equivalently, like I mentioned, you need to keep the critical path as little as possible, the data request flow path, so that you don't incur the additional cost of latency due to network hops, or the additional cost of having to serialize, deserialize these requests through the additional middle layer. And it is very similar to how IP routing and routing tables at internet scale work, where as your request packet flows through different routers in order to reach the right IP address, they just peek at the request header and make the decision of where to forward the request. And third, when we talked about gRPC and REST protocol, that is slightly analogous to how the load balancing and the layers of internet load balancing works, all the way from like network layer to application layer. And they all serve different purposes, and you need to choose the right protocol, and that can shape how you architect your system very well. Hope this was very interesting topic for you. I'm presenting this as part of the Internet SF Day, and it focuses primarily on the machine learning model request routing problem. If you want to go a little deeper into this is the Netflix blog post that I mentioned, which this presentation is based on. And the other technologies that I mentioned to you in this presentation are also available here. Thank you so much for listening to this talk, and have a great rest of your day. Thank you.
Hello and welcome back. Our next speaker, Kevin Cameron, is going to present From Monolith to Chiplet, IPv6 Virtual Networks as the Universal Hardware Abstraction.
So I'm Kevin Cameron. I generally work in EDA tools for chip design, particularly simulation. One of the things I've been looking at is how do we create hardware from software, and software that runs in networks. So we're large jobs like AI, LLM type tasks, generally spread over multiple machines and running very parallel, and it uses networking. So as somebody trying to make chips from hardware description languages, normally I'm interested in switching that to software defined hardware, where we take advantage of networking tools and things to convert software into hardware. And one of the things we can do is leverage the fact that IPv6 is an enormous address space. You can give every individual transistor in a large system its own IPv6 address and tie that into the rest of the world at the same time. So initially I was looking at how do we do things like federated simulation, where we use multiple simulators in a network space to create one big simulation. And this is the sort of extension of that into, given that we have the simulation or we have a software task that's running parallel in the network, how do we turn it into better hardware for the same task? So the general approach that I'm looking at here is that if we have a monolithic application or one that's running parallel already, can we fragment it into more parallel pieces so that we can look at the communication? And the way you can do that is anytime you see a routine call in code, you can treat that as message passing between contexts. So if you tag the ends of that call or callee at IPv6 addresses and create a socket between the two, you can measure sort of what characteristics a particular routine call has. And we're doing this in the runtime where we're seeing the data transfers and not in static code analysis. when you have a pile of containers, messaging each other, you can try moving them around in the network and allocate them to particular hardware that maybe has some acceleration. Once you've got your containers where you want them, you can then look at how to turn the abstract IPv6 sockets into the best physical implementation of that socket connection. So we can look at down here as taking your code that currently runs as an executable spec of what you want. And we're just going to take, regular C, C++, Python code, Java, whatever you happen to have. And it's running on x86 or ARM standard server machines. And it's also using lots of standard libraries. So trying to avoid things where you already have a specialist stack, but we can do that too. And most of the code we're expecting will be defined sequentially rather than being heavily parallel, although it might be a parallel job. So we're good to run it, see what it does. And we're looking at the opportunities to find parallelism in we can take any routine call or API libraries and use that as a cut point. We can also, in the runtime, look at how you're accessing your data and take advantage of that to exploit locality when we move things around. So sharding into containers gives us advantages in isolating pieces of code, and we can do things with the networking between containers fairly easily. It's kind of user space operations to work on the networking between containers, and we can move them around easily because they're small versus a virtual machine or an entire actual machine. You can stop container, move it, you can replicate it. It's easy to play with. Open source tools like Podman, Docker, and other stuff work for Lisp. One of the things in hardware design is that hierarchical names for things are used in hardware design, like languages like Verilog. That's a good map for DNS. So if you want to look for something, you just use the hierarchical name and it'll translate to an IPv6 address for you. So you don't really need to do a lot of work to support that. And again, standard socket interface for communicating between things. That is a fairly abstract thing in itself. The implementation of a socket is not something the code needs to see, and you can change that in the background as containers move around. Again, anytime you've got an API boundary, routine calls can be turned into message passing. You do want to do lots and lots of channels. This is why IPv6 works. You're not going to use single, IPv4 type addresses and then lots of ports. You're going to have lots of individual IPv6 addresses and channels between them. And you may have more than one channel between two IPv6 addresses. You're trying to tease out the behavior in each socket channel and then be able to optimize how the networking is done around that, whether it's low latency or high throughput. Managing all your containers within a VLAN just makes it easier. That's part of some of the IPv6 protocol stacks. They will do VLANs for you fairly automatically, and it lets you sort of dictate security around how your container pool is working. Our variation on just treating all routine calls as message passing is a specific case of C++ or other object-oriented language method calls. So you can give the objects in memory their own IPv6 address, and then sending message to that is equivalent to doing method calls. There are some advantages in that, because if you're doing virtual function table driven method calls, you can sort of dynamically replace virtual function tables with different versions that do different things and send messages to different places. This is particularly useful if you want to short circuit the paths that are used in implementing socket channels. Again, you can use the DNS name hierarchy approach to finding your IPv6 address for an object. One of the reasons for doing this kind of stuff is that RISC processors are actually not very efficient on large amounts of memory. So you want to shard your application into pieces where you're working inside the cache limits of the RISC processors and not missing cache. So you kind of want to get everything down into very small pieces that sort of meet that criterion, and then you can look at whether you should reassemble a bunch of containers which are sort of closely associated back into one container, so that the calls are correct and not going through message passing. So common patterns in code that you could take advantage of are things like list processing. So if you use standard packages, like C++ ones to do your list processing, you can catch those in the runtime and say, okay, I'm going to shift the implementation from top-level call to a list processor out to a SmartNIC, and the SmartNIC will then translate the ongoing calls to other objects as message passing. I can do them in parallel. So this is where you're looking to implement the C++ library on the SmartNIC and have it manage the list data for you. So this is where you containerize the piece of list processing and then move that container to the SmartNIC. The SmartNIC is not having to do major support for all of C++. It's just looking at efficiently implementing particular list processing functions for you. And you may have a lot of SmartNICs that can do slightly different flavors of that. So overall, what we're trying to do is see if we can fragment what we have as fairly monolithic applications into a graph of nodes that are sending message to each other, where the nodes are quite small. And we're running that in a kind of virtual machine environment. Like it's sort of like an operating system that spans multiple machines. In the OCP world, we call that the graph virtual machine. And we're looking to find out, for every message passing channel, what it needs in terms of performance. Is it something that requires low latency or high throughput? And then after we've gathered all that information, we can say, okay, we need to bind certain nodes together. So basically the nodes are going to be across a whole number of containers, but we may want to reduce the number of containers by coalescing nodes together because they have latency issues. I mean, generally in circuit simulation, which I do, low latency is key to parallelism. So you're going to see a lot of things where they'll want to be in the same container. But if the hardware you were designing is something like a pipeline processor, it may be just throughput as you go from stage to stage. You're hoping to get that information out of the initial runtime exploration. And then once you know what you're doing, you can just move the pieces of code together and put them on the hardware they need. And then, your final step in that is sort of redoing the communication piece. So reallocating the sockets where you haven't sort of turned them into direct calls. You try and make them as direct as possible. So it's like fragment into an analysis, do the analysis of the message passing, coalesce nodes, which may be neurons, together, and then finally, short circuit the communication paths as much as possible to reduce latency and improve throughput. As I mentioned at OSP, we were considering this kind of analysis with a graph virtual machine looking after where all the code is. So basically In this version, the GVM is managing those containers, and we're looking at the graph being all these compute nodes with message passing, and from an AI perspective, it looks a lot like spiking neural networks and neuromorphic computing, where one of the ideas there is that you do not want to be doing work if you don't have to. So you're trying to save power by fragmenting into pieces that can sleep most of the time. And the graph virtual machine is essentially a way to get your work done that way. Again, the risk scores don't really like having a lot of memory, so you're trying to find nodes in the graph where you can keep the memory footprint to a minimum, and maybe if you've got nodes that are much less than like 2 megabytes, you might merge a bunch of nodes together to get up to that 2 megabyte mark, which the processors can handle well. In something like SpinCloud, the Spinnaker 2 chip, I think the amount of memory each RISC-V processor has, ARM processor actually, is somewhere like a couple of hundred kilobytes rather than 2 megabytes. But principle applies that if you work in that memory rather than like missing cache, it's going to work a lot more efficiently. So just to reiterate on IPv6, we're using technology that has been developed. This is technology that has been in the marketplace for a number of years. Standard code, the concepts, VLANs, containers are all there and working. The DNS name mapping stuff is there and working. So we're not doing a lot of work here reinventing things or inventing new things. We're just leveraging the environment that IPv6 has given us. And we're looking at taking advantage of other things in the environment that the cloud people of cloud services people have developed, for their data centers. So things like virtualization, Hyper-V in Windows. You can see it's fairly easy to sort of create a VLAN, create a virtual machine that matches your VLAN, build a pile of containers in your virtual machine, and then say, okay, now that I know what my containers do and how they talk to each other, I can move them out onto proper hardware. So you can see the sort of, with the existing infrastructure, there's not really a lot of work to do here. And with AI helping you write the code, it's not going to take long at all. So when you're actually working either in a good software-defined networking environment or the virtual environment, you can play with how the socket channels are are working in terms of latency and throughput. So you can pick a particular channel and just make it take longer to get messages through that channel and see how everything reacts. So if you do that and you find that the overall performance is not changing much, you may have found a pipeline structure. So things like a GPU pipeline, the latency between stages is not that important. So you're looking for when do you have that behavior, and then allocating the right kind of hardware for handling that particular flow. And you can hop between machines. So you can take something like a GPU pipeline and say, okay, we visit this one as an FPGA pipeline where we're hopping data between boards because the FPGA can do a fatter pipe than the GPU can do on the same AI application. As I say, the other thing with the containers is you can sort of do things to work out, particular characteristics of containers, like, whether the data in them needs protected or not. And these are things that, as you move stuff around a network, you can have criteria about particular containers, so you can't do things like put it in public space or or the opposite. You can say, okay, here's the public piece of thing, here's a private piece, and the boundaries should drop out naturally when you're doing the profiling if you're fiddling with how the channels are working. So just reiterating that, we're looking at taking the information from profiling and driving the containers into particular configuration for best behavior. So far, this is still the same original code you had. We're just playing with how the code runs. So we haven't modified the code at all. Sort of trying to do this piece. We may look at what's in the container and say, okay, we should recompile everything in the container for different hardware. So you may want to switch something that started in x86 into something that's ARM and FPGA as an alternative. So one of the application areas here is can we take the thing that we've managed to reconfigure into its best parallel form into new hardware. So we're looking at what's the reliability requirements on message passing, for instance. So there was a group at this Open Compute project looking at more reliable Ethernet. So the question is, do you need more reliable Ethernet on a particular link? And other things like, okay, when you're doing message passing, there's equivalent to calls. Is there a return? So sometimes there isn't a return. You don't care if they're being returned from a routine call. So some channels are going to be bidirectional, some are going to be unidirectional. That should be teased out somewhere. And another thing is there's a mapping between sort of IPv6 and different implementations. So you can do IPv6 over PCIe if you want. So sort of you can have boards which are accelerator boards, which when you plug them into the system, just look like something on the network, rather than being something on the PCIe bus, which need special drivers. You can say, okay, we'll do generic drivers which make this thing look like a network attached device, and then we'll deal with the PCIe direct mechanisms once we know what we're actually doing with the hardware. And new systems coming where you want to be able to replumb things. Got optical computing and communication. We've also got people trying to do millimeter wave communication, where the reliability and throughput, bidirectionality, and those things is different from standard Ethernet. When we're picking the protocols to go with the channels available with physical hardware, it's kind of the approach here. We should probably add that millimeter waves is being proposed for doing communication within the rack. So it's basically millimeter wave radio does not get through things very easily. So it's easy enough to have one rack using it and not interfere with the rack next door using it. It is millimeter size, so it's plumbing when you're using it. It's piping stuff around. Literally, some of the design tools for that probably aren't in place yet, but it's a lot easier to work in millimeter wave and free space optics than it is to get all the cables in. In both free space optics and in millimeter wave, you can use frequency to separate out channels. So you can get an awful lot more channels, which corresponds again to the advantage of IPv6, giving so many different endpoints, and basically have billions of channels, literally in most IPv6 virtual world and in the physical world with a millimeter wave and free space optics, frequency and color variety. So in the OCP work stream I'm in for AI hardware software co-design, we're particularly interested in neuromotor computing, and SpinCloud is one of the available hardware platforms for that. There aren't many deployments. And what we're seeing is that people who build AI hardware tend to build their own software stack to go with it. So while SpinCloud is actually general purpose hardware and it's just a big mesh of ARM processors, the software stack available for it is focusing on spiking neural networks and nothing else. And then other applications which are very similar to spiking neural networks, like event-driven simulation, are not supported. So what we're looking at is saying, okay, we can do something where we just make SpinCloud support containers, and then this other stuff is going to work for you. So this is a picture of SpinCloud's Spinnaker 2 board, and it's a big array of chiplets, where the chiplets are stacked ARM processors and DRAM. So in this kind of setup, you could actually use stacked chiplets, including communication or like free space optics or millimeter wave on top of the stack, which would get you to the next board if you have multiple boards arranged on top of each other in a rack or beside each other. So that's where you get to take advantage of the bandwidth of free space communication. When you have a stack of boards that are able to talk to each other face to face, you're able to like take advantage of the fact that the face to face distance is a lot shorter than the copper path, and it's not being shared as much. So it will give you a huge boost in performance. Again, what you're looking for with the spiking neural network hardware is that most things are just sleeping, and the activity is, it's like you will see, something changes on input, it'll ripple through boards and messages get sent to neighbors, either on the same board or for stacking and doing free space communication to the next board. But you're looking at something where even the communication will be asleep until it's needed, auto diamond. That works okay with optics. If you're just firing the neurons every so often, then the inefficiency of using an optical system, which is quite high, versus like short range copper, doesn't matter so much. You're just not using that much of it most of the time. Other things you can do in this kind of environment is add redundancy by using multiple containers at the same time. So since you have control of the network, you can say, okay, stop sending messages to my container, I'll replicate it. So I've got 3 the same, and then restart the messaging. And in that environment, those 3 containers should be doing exactly the same thing all the time. So you can then look at the outputs and put that back into the network and say, hey, take these as a voting group, and you need to get 2 answers the same before I'll pass that information on to the next thing. But that's functionality that you can get without changing any software. You're just tagging the containers in ways to make that happen. In summary, you were taking your monolithic app, running it, seeing what it does, and then we're going to optimize how it runs. But IPv6 is the enabler for this. That hardware is in place, a lot of it's software-defined networking with SmartNICs. So we have all the pieces to do this already. It's the internet protocols that have enabled it. So while the initial intent here was to get to custom designed chiplet systems from regular software, the stopping point of just getting onto heterogeneous computing platforms is sufficient goal in itself, I think. And I'd say, we could do that now if we want. It's not that hard. And the next step is probably not going to be that much harder given the ability of AI these days. And as we said already, IPv6 is one of the key components of doing this that's already being built.
Hello and welcome back. For our next talk, Ronald Petty will present why Q-Day is today, preparing us for the imminent use of quantum computers. Welcome to my presentation on why today is Q-Day, getting ready for quantum computing. Again, my name is Ron Petty, and I am with the San Francisco chapters of the Internet Society and the ACM. So our agenda in this talk is to describe a little bit about what Q-Day is, how does this relate to similar events that we have planned for, if there are any. We'll see why it's important to you, not just from a safety perspective, which is what most people are aware of. If you're unfamiliar with Q-Day, we'll have some background on this, but also just to kind of motivate us to working in quantum computing in general. How might we go about doing that? And that's actually what I really want to convey here. We'll also talk a little bit about what is going on in the state of the industry of quantum computing. And then we'll try to tie it all together with why today. We hear about Q-Day being into the future, maybe 3 years from now. I am going to try to convince you otherwise. And then we'll look at how we can prepare through a set of training, through a set of simulation and available hardware that we can get as non-experts. All right, so why is Q-Day important to you? I'm speaking on all of our behalf. So I should mention, I am not an expert in quantum computing. I have a passing interest, and I am trying to educate myself more every day. But I am one to pay attention to trends and evolution of technology. So it has crossed my radar, and I hope to convince you it should cross your radar. So a typical reason to concern yourselves with Q-Day or quantum post-quantum encryption day is harvest now, decrypt later. The idea is through this new architecture of computers, quantum computers, they will be able to store our encrypted data today and in theory, decrypt it at some point in the future. Now, the concern is this point in the future used to be very far away. And as time has progressed, that point is becoming sooner. And that's why this should be on your radar. Additional yet related concerns are breaking digital signatures. These are the things that represent us on the internet and services, so we know who we are when we're talking to each other. Another concern, as an example, will be the breaking potentially of the encryption used by cryptocurrency. So this can influence how the voting is done and many other aspects of it, which will then impact the ownership potentially of crypto. And so you can tell that a lot of this concern is around security, and that may sound scary, and it is, but that's not the only use for this, right? We'll talk as we go through here, but one example will be to help model new vaccines, new chemical compounds. These kinds of things we will see as we get bigger. Quantum computers will be doable. We'll be able to get to vaccines that may not have been easily created with a classical computer. So this seems bad, this coming Q-Day and the breaking of encryption. Is there some other story we've seen before that kind of relates to this and how we may approach this? Well, one that comes to mind is Y2K. So for those who were born after 2000, this will be new to you. So Y2K, in short, the idea is computers, for various reasons, largely around just optimization of storage, had a short date variable. And the format was we could just store the current 2 digits of the year. So if it's 2026, we would just need to store 26. But in the 1900s, we assumed it was going to be 19. We didn't really think about the coming century, the coming eon, where the clock would roll over. So in theory, we could have went from 1999 back to 1900, which would have been incorrect. Other systems may have failed in other ways, but that was the concern, right? And so systems that have clocks and schedules and calendars, this was going to lead to a whole bunch of problems. So there's a link there. You can please take a look at that and see how society talked about this all over. Some people were very concerned, others were not so concerned. There was a lot of efforts to update code to deal with this issue, but in the end, it wasn't catastrophic. You could kind of say that the planning and the concern is what made it not catastrophic, but of course there's counter arguments to that as well, and maybe it just wasn't as big of a problem as we had thought. So is this the same level of concern as something like Q-Day? It is yet to be seen. For those who were alive in 1999, it seemed you heard about Y2K all the time. Now, this is a bit of my personal opinion, I don't know if everyone's heard of Q-Day, right? We've heard vaguely of quantum computing. This is something a little more specific. And so it's a good thing to have on your mind. So what can we do to prepare, at least in the case of security? So the good news is the two kinds of computing, we have classical computers, we'll call those non-quantum computers, and we have quantum computers. Both, we believe, will have techniques to protect encryption going forward. And so in the case of classical computers, we call that post-quantum cryptography. And in the case of a real quantum computer, which you may have access to, we would, in those environments, install ciphers that are quantum cryptography ciphers. And so what that should tell us is there's a variety of techniques that have been engineered through lots of collaborative efforts and a lot of testing and a lot of theoretical research. None of them are 100%, but as time goes on, as we test things more, PQC and eventually QC type algorithms around encryption will start to hopefully merit the belief that they will protect us. This picture shows us from Mosca a projection on when should you care about Q-Day. So you can see kind of this formula, x plus y is greater than z. And so it just mentions here, x is how long do you need encryption to be secure, right? So if I want this to be encrypted until I'm long gone, you have to calculate those years, right? And then y is how much time will it take to retool the existing infrastructure with large-scale quantum-safe solutions. And so this is the part I want to highlight, is us actually preparing ourselves, right? We desire long forward-facing secrecy, but that takes us education and effort and execution to actually make that happen, right? Then, of course, you balance that with what the prediction is for when these quantum computers are going to be able to break our encryption. So, what is the state of this ecosystem? So I've kept this simple. I've looked all over, pulled lots of information together, and decided to not kind of inundate a flood of information, especially when it's changing a lot and there's better resources online. But what I will kind of simplify is the story. So my belief is that the quantum sector is growing, not just because it is, but because money is flowing into it. We hear about larger investments, right? Normally, finances, people are very smart. They're not going to necessarily invest a lot of money in things that are going to fail. Sometimes it happens. And so it's not just theoretical, interesting development, right? There's actual evidence that these systems are working as advertised. The technology is getting better, and thus the investment keeps perpetuating. And so that continues. So we've seen some consolidation in the sectors. You can see here with D-Wave. The government has also funded recently $2 billion across a variety of companies to keep this going. So what is going? And so that's what this image, thanks to some blogs by Google, is showing us. So I'm going to kind of paraphrase what this one paper was referring to and what we see. So on the left, we have physical qubits, and on the right, we have Toffoli gates. And basically, these are showing us the belief of what we need to reach something like Q-Day. So years ago, we believed we needed a huge number of these physical qubits, right? The bits is what is inside of these quantum computers. Now, the belief is we need a lot fewer of these, right? So that's why it's going down to the right. Normally, you see a picture about qubits and you want to see more is better. And I think that's true in the general case. But when it comes to how many is the minimum we need to break something or accomplish something, that's what this is showing us. So on the left, it's kind of in reference to the actual physical qubits. And on the right, these gates have to do with error correction and those kinds of aspects of these quantum computers. So there's this down into the right trajectory, means we need fewer of them. And because we need fewer of them, things like less incorrect answers are generated, solutions are doable with a decent size system. We don't need a million qubit system maybe to do some of this work. So that's really what needs to be shown here. So again, we hear in the news about the increase of qubits, but this is highlighting, logically speaking, we don't need as many for various reasons to maybe reach Q-Day. In other words, have a smaller quantum computer to break encryption. And it's not all bad. It's not just about breaking encryption, right? It's also about, can we solve other problems, like, again, maybe in chemistry or medicine. And so again, if we can build higher fidelity, smaller systems, that's a much more reachable goal than necessarily a million qubit system. So again, that utility is increasing while the systems in theory may actually get smaller. So why is Q-Day today? So I wanted to kind of parallelize this. One is Google and others believe this breaking of encryption is within potentially a few years. 2029, 2030, that time frame. Now, this doesn't mean it's going to break everywhere, but that's kind of what the trends are showing us with these new architectures, improvements in techniques. So what that means for us, and this is why even Google has announced that Q-Day is coming, you should start preparing. We need to learn as engineers and users of computers and being on the internet, what does it mean to be safe today? What are our options? Now, I don't have a lot of slides showing that. We will give you offline guidance through a PDF where you can go and do your own research. But basically, there are techniques that we can be potentially doing, and I'll start to show some of that here in a moment. So one is are we using post-quantum cryptography on my computer today? Did I even have to change anything to take advantage of that? Now, these aren't foolproof demos showing that, yes, we're using it correctly, yes, it's protecting you, but it is to start to show you how you can find out what your system is doing. Okay, so again, safety, are we using it today? And then just the general statement, forget about PQC or Q-Day in general, is my data safe? There's other ways to decrypt data, right? We can just brute force it with very large computers, right? And there's very smart people out there that are finding how to use classical computers to decrypt things. So it would just be a good practice, even without quantum computing, to understand what is our risk profile when it comes to data. And that includes transit and storage. So again, execution, thinking about where these ciphers are used, how they're used, how do we prove them, right? The confirmation of it, all this takes time. Teaching our colleagues about it will take time. And so even though 2029 is 2.5 years away, that's not very far, especially on a set of technology and techniques and tools that's new to most of us. A lot of people don't even know what regular non-quantum, classical encryption things look like. Plenty of people do, but there's even more who don't. And so what can we do to help them? And we've had projects in that space, right? We have Let's Encrypt. The Internet Society has lots of guidance around this. The EFF, the FSF, lots of groups talk about these things. But it can be hard to find good resources for my needs today. So that's safety. The one that I want to add to this conversation is just learning in general. It's not all bad. Q-Day, to me, shows us a maturity of quantum computing. And by having a new form of computation, we have lots to learn, lots to take advantage of. There's going to be complexities where these systems work together, classical and quantum, to do particular algorithms. So that's another level of complexity that a lot of us were never exposed to in a computer science program. So now's the time, regardless of your age, to maybe go back to school, right? Learn how quantum computing works. What can you practically do? What you might not be able to do, right? We may not, on an individual level, be able to purchase a quantum computer for one reason or another, maybe cost, maybe regulations. It's to be determined. You know, today the market looks a certain way. Tomorrow, who knows what it's going to look like. But we can teach and educate ourselves today. Are there tools that we can actually practice with and start to understand this? The answer is yes. Again, myself, I'm still fairly new to this, and it's ever evolving. So again, start at the beginning. We have some resources to look at in just a moment, and we'll show you some example of some tools that are actually working on my computer, just to convince you, hopefully, that you can run these things on your computer. Okay, and then over time, you'll get confidence, right? You'll be able to manage your own environment. You'll be able to teach the next person, and that's how it goes. And that's what we really want to highlight here today at Internet Day. All right, the safety problem is urgent. 2029. Learning is a lifetime. No day like today to start. So what resources are there? So again, this is a little bit opinionated. I've asked around, I've done some of these tools and simulators myself, tried to make a short practical list that will work hopefully for you. Some colleagues of ours in the ACM, Will, thank you for this. He recommended Black Opal from Q-Control, which is a training environment for quantum computing. It's actually very nice, easy for the beginner, but it actually is very comprehensive. So great resource. There's other ones as well. The book Quantum Computing for Everyone is a pretty quick read, under a couple hundred pages. Does have a bit of math, but that's the reality here. If you're going to learn how this works, you got to have a bit about the physics, a bit about the math, a bit about the hardware, a little bit about classical versus quantum and where they intersect. It's a very good book, short read, and you can, not that I'm recommending this, but you can even kind of squint your eyes in a lot of the math and still read a very good narrative through the whole book. And then when you're ready to try a little bit of the math, you can go back and take advantage of it. Then of course there's many more evolved in-depth books, much more hardcore than that one, but considered one of the gold standards. All right, for the practicing, what can we do? Well, one is we have simulators. So I can't claim to know all the details here, but basically a classical computer can simulate a quantum computer. For every qubit that you add to your classical simulator of a quantum computer, you double the amount of data that you need to manage that process. So in other words, it's exponential in the amount of, we'll say, resources needed in a normal classical computer to represent or simulate a quantum computer. So that's one of the issues here that many people are working on, is how can we simulate 1,000 qubit quantum computer on a regular computer, because there's just a lack of that hardware and accessibility to that hardware. Now, it turns out we do have some accessibility to actual quantum computers, thanks to, for example, IBM. So you can actually create an account, you can launch access to a quantum computer and make a small example program and actually run it and get the results. So again, the point here is we have books and class-like material. We have simulators that can simulate small quantum computers on our classical computers. And then we even have access to real quantum computers currently through the Heron V2 chips at IBM. And there's other resources as well. But these ones all worked and relatively inexpensive, except for the book, and if you want to pay for the advanced class. And again, just to kind of tie it together, this image may be a little hard to see, but on the right-hand side, this is a Chrome browser going, in this case, the Q-Controls website. If you go to security and look, you can actually see that it's using a quantum proof cipher. And so there is information out there if you're interested. Chrome was one of the early adopters of using PQC type algorithms in its encryption. So again, this is just showing us that I can take a standard Chrome browser. I happen to be on a Mac, and you can actually look for hints of the use of quantum technology, right? So it itself is not quantum, but the algorithm is meant for Q-Day. And there's a lot more details than that to it, but just be aware, there are people working on this behind the scenes, and I, for one, appreciate it. It's good to see this in action. So what else is there that we might be able to just kind of do locally to confirm the technology? Now, this doesn't show all the setup, but what this is trying to show us is the use of SSH to connect to a remote computer. Now, in this case, this just happens to be on a local virtual computer through Docker. I run a SSH server. So if you're not a developer, don't worry. All this means is I'm on my computer in the terminal, and I can connect to a remote computer and be in their terminal and keep typing. But what you want is for it to be encrypted as we're over the internet. So what this first one here in red is, it's showing that if you don't do the proper setup, you will use, in this case, it's an ecliptic curve cipher, and that's great for encryption, but it's not great necessarily in a Q-Day world type event. So can we use a PQC type cipher? And the answer is yes, and that's what this bottom case is showing us. So it's a little hard to see, but right above the white box, there's a Kex algorithm, SMTR up 761. And it mentions there in the box, this is a post-quantum key encapsulation method, but it's also a classical elliptic curve, just like the top one. And so why is there two? This is just trying to show us the complexity here. There's the classical world, which is the top there in red, which still works today, mind you. And then the bottom is both. And I mentioned earlier briefly that the post-quantum encryption and the quantum encryption algorithms are still being developed. We have a very strong belief they're going to work, but we're not 100% sure. We're not fully believe that they're going to work as maybe as we are with traditional encryption in a traditional non-quantum environment. So it's a hybrid. And so that's why it mentions it's hybrid PQC. It's a combination of the old way and a new way. And the idea is if the new way fails, we can at least get some level of protection by going back to the old way. And that's what this is showing us. Could we do an actual non-hybrid approach on a classical computer? Probably not. Again, because of exponential growth, like how many qubits do you want to simulate, and then with that. So again, it would take a very large computer to have a pure quantum cryptography approach in a classical computer. So we have to go with this hybrid approach. And again, I'm not an expert in the ciphers themselves here, but really it's about knowing where to look, have a general understanding of what they're doing, and then we can go do our own research. We can check, is SMTRUP 761, is that still secure based on the latest knowledge? How is the ecliptic curve stuff holding up in relation to the progression of Q-Day? Right, now we have things we can start looking at. All right, as promised, I wanted to show some of these simulators in action. And again, with the small time we're together, I can't really explain all the details of quantum computing, but I really just want to motivate you to show that these tools actually can get installed on your computer and can work, give you a little bit about what they can do for you. All right, so let's start with one of the simulators. So Q2NS is as it says, an extensible quantum network simulator built on NS3. So NS3 is a popular, we'll say, network simulation tool framework. And through extension, a team has built the ability to model quantum computers and networks on top of that. So there's a lot to this. But what I want to show, and this is out of a university in Italy, very, very good talks online if you look around for it. So what I'll show you is launching of a kind of pre-canned server environment so you can actually kind of visualize what a quantum network may look like, including the entangling, the transmission, what does that kind of look like, to give you some kind of visualization. And there's more to it than that, but again, we'll keep it high level here. All right, so I'm just going to the terminal and I'm going to launch the Q2NS visualization service. So this is from a Git repo. Again, all the steps will be posted online on the Internet Day SF website. All right, so stop the one that was running before. All right, bare bones UI, right? The important part is about quantum modeling here. So let's just go through the examples. There's 4 of them. I'm not going to comment too deeply. I just want to kind of show you these visualizations. So we'll do load examples. And here you can see the 4 that kind of came with the system. We can always make more. All right, so the first one is the Bell pair distribution across a fully connected network of nodes. Okay, again, without knowing quantum computing, may not be clear what this is, but we'll just say we're sharing qubits, and by sharing them in a certain way, we can we can make measurements and understand what we're trying to say to each other. So again, trying to keep it simple. All right, so let's load this. All right, so key thing is in the bottom right, you'll see the activity. So I'm just going to do it step, and you're going to see what's happening in the bottom, and it'll be visualized as it goes. Okay, so again, this is the bell. All right. Initializes 1 bell pair. Okay. Entangling, transmission. Then, so that's over a quantum network, right? So what is a quantum network real quick? This, for example, could be sending of a photon on a fiber optic channel, okay? Next, over, could be fiber, but we'll just say a classical network, non-quantum network, is confirmation that we got it, okay? So that result kind of gives us clear to do another one. Entangle, send it, confirm. Okay. And now we're making a full mesh here. Everybody's going to have a related pair. There goes the ACK. And there we have it. As it says here, all Bell pairs distributed and confirmed, a full mesh entanglement established. Okay. Again, without reading the book, going through all the details, this may be a little hard to know what's going on, but here we can kind of start to visualize these things. This is good if you read the book, you can start to envision how this all works. All right, let's try the next one. All right, next one, gigahertz state generation and qubit distribution to remote nodes. Okay, same thing, we're just gonna go through next. Notice there's 4 nodes this time. Okay, set up 4 qubits. Applying a gate, tangle, tangle, tangle. Sending the first one out, second one out. Notice the acknowledgements are coming back independently here, trying to show that these are kind of operating on their own at that level. Okay. Okay, here we have the resources confirmed by all nodes. Again, without reading the book, we're skipping some details like what is C0, what is the gates about. Again, this is just trying to show utility of this tool. Okay, next. Distributed graph generation via centralized orchestration. Okay, so different layout. Again, if you're in networking, you can start to envision like, all right, who's talking to who, right, for routing and things like that. Okay, again, set up some qubits. Tangle. Send, get the acknowledgements back. Now, in this case, we're showing remote setup. So we have an orchestrator setting it up, this external network. So a slightly different view compared to what we saw two times ago. Okay, so different way of managing the distribution here of the entanglement. Okay, the last one, quantum teleportation of a qubit using EPR, pair and classical corrections. We'll just hit play and let this one play on its own. So Bob and Alice. Speed it up a little. Nope, speed it up too fast. All right, Bob verifies teleported state. Okay, again, read the book, check out the Q2NS simulator. It's a useful way to start seeing how these things work and maybe understand what they're talking about, in the math in the book. Okay, next one we're going to take a look at is a different framework called Cirq from Google. So this is a framework that is allowing us to do local simulation and represents Sycamore and Willow and the other quantum computers that Google has been working on. So for here, we'll jump to the terminal and I'm going to run a small example here. I'll show you the code in just a moment. Let me zoom in here. Okay, actually, now I will zoom out. All right, so a couple of things here. One is it's dumping what the device is. So this is a representation of a grid-based quantum computer, in this case, the Sycamore quantum computer at Google. And you can kind of see, just to give you a little idea, it's representing the connections between the qubits. Not every architecture is going to have every qubit talking to every other qubit. Not that that's how it's done, but that's what we're trying to model here. And you can kind of see it's like a coordinate, right? So it starts at 0 and then going down is 1, 2, 3, 4 all the way to 9. And then on the left, same kind of thing, 0, 1, 2, 3, 4 up to 9. So again, this is a grid representation of the architecture of the Sycamore system. And then in this case, we built up a circuit to simulate and it visualized it here. So again, it talks about gates and the qubits that are the input, and then we get a result. And again, too much to get into, but what this is good for is we can simulate small circuits, quantum circuits, execute them, and then get a result. And then ultimately, these kinds of tools will allow us to not just do a small modeling locally or even somewhat larger modeling, but allow us to probably send it to real hardware, like we'll see in the case of the IBM example in just a moment. So what does this look like real quick? The code, just to show you that it is just code. So we can see there's the Cirq framework, again from Google. Here we're using the Sycamore device and laying out the particular grid pattern and tying it to these input qubits. Then we'll do the simulation and the estimation and print the results. So very short program. Again, it doesn't really explain what it's doing or why or how. Again, don't have time for that in this talk. But again, I really just want to highlight, this is showing us that we can do things like this, right? The next thing you should do is go take that class, go read that book, then start to come look at this. You know these tools work on your computers, right? I didn't have to pay for any of this, neither do you. Okay. Last one we're going to take a look at is here at IBM Quantum AI Platform. So you can create an account for free. It doesn't ask for any kind of credit card. And what it allows us is actually 10 minutes a month. In this case, it looks like we're going to get 1 month, so just 10 minutes of actual real quantum computing time. So this is different than just the regular simulators. So now it turns out I've already set this up via a Docker container. So let's see if I can show that here. So a couple things. Again, I'm just giving you the high level. The details will be on the website. So this is a Jupyter container, right? So just running Jupyter. And then from the IBM website, we download a notebook, a Jupyter notebook, and load it here. So that's what we're cobbling together in this particular case. And so that notebook looks like this. So actually, let me take one step back. Once you create an account, you can find the notebook on the website. So there's documentation. You can see here on the, kind of the hello world example. See here on the right, there's a download. Oh, sorry, my image is in the way. There's this download notebook. And so you download it on your computer, and then because you have Jupyter running, you say upload it, and you get this. Now, again, things change. So if you don't know Jupyter and you don't know these things, this may be a little hard at first. But just this is the interactive Python environment. It's allowing us to run blocks of Python. But like all code, this may need a little help. So for example, you may need to install some libraries before it works. So for example, it does tell you need the Qt IBM runtime, but this Docker container, because of my environment, didn't have the Python visualization library needed. So once I aired out, I knew this, but again, this will all be documented in the other doc. All right, so you take this notebook, you get a key from your setup. So you would get a key over here. You say create key, and then you would get back over here into the notebook, and you would use it. Now don't use my key. I'm going to delete it so you can't use it. I only have 10 minutes anyway. And so once you've done that, you will do something similar to what we just did in Circ. You will describe a small quantum computer circuit. It will then, here in this case, we're just visualizing it. So that's what this code is basically doing. Everything else was libraries and the API keys. So we create this quantum circuit, talks a little bit about it. Talks about how we'll do measurements. Again, without understanding quantum computing, this may be a little obtuse, but just be aware we'll call them techniques to do the reading, okay? And then this actually ties back, interestingly enough, back to the presentation. This is showing us that we want to optimize that circuit we just designed. So even though it looks a certain way, may seem simple to you, the reality is this gate, for example, may be combined of many qubits and things. So ultimately, we want to optimize it. So there's algorithms to, we'll say, reduce this complexity, and that will give us less error just from the physical nature of how quantum works and just this ever evolving new hardware. And it'll be faster because there's fewer pieces, right? And so anyway, lots of reasons to optimize. And so you run it through an optimization step. Next is to actually execute it. So there's a couple ways we could do this. One is we could simulate it if, again, the circuit is small enough. Again, not really on the real hardware. Or we can actually use the real hardware. Okay. And then once that's done, we can get the results back. And again, interpreting, you can see the bottom, there's those measurements methods we used. And we can get a result and visualize it. So again, that's not the important part right now. The important part is this actually ran on a real quantum computer over here. And so that is what this is. So I'm just going to click on it just so you can see what it looks like. So basically, as it's running, you'll see this dashboard, and it'll say pending, or if it's running, it'll say in progress, and eventually it'll say complete. Now it takes a long time because we're fighting for resources, right? We're not the only ones using this free resource. So even though it says it only took 12 seconds and 20 seconds total of the 10 minutes you're allotted, it may have taken 5, 6, 10 minutes to actually fully execute. Okay, and what you can do is you can see the various measurements mechanisms. Now this is a different one. I ran a 100 qubit test, which is also very impressive. And that's what this is representing here. So unlike the hello world of Cirq, which was nice in the terminal, here we have a nice UI showing us features of this quantum computing in the computation itself. Okay, and then we can get the results, and if there's issues in the logs, we can see all that up here as well. Okay. Okay. And that is the end of my talk. Thank you for attending, and I hope this inspires you to try some quantum computing and study on your own, and see you next time. Thank you for attending Internet Day. We hope this inspired you to participate in our local chapters or to contribute to your own local chapters. We hope to see you next time.